Okay. So basically today I'll finish Laplace equation. Yeah. Okay. Okay. So today I'll be finishing Laplace equation concepts and all. Uh, Finish Laplace equation. So to just uh, to just basically understand where are we headed. So basically this course is basically machine learning. Is about machine learning algorithms for PDEs. So in this particular set, I had to finish all the concepts of PDEs and all the concepts of machine learning, which is basically amalgamation of linear algebra, real analysis, optimization, probability, and so on. And for PDEs, and we had to basically apply these concepts to our PDEs. So for PDEs, you needed to know something called solution space, called Sobolev space. And right now we are focusing on Laplace equation. Next, we'll move on to elliptical equations. Then we'll move on to PDEs, heat equation. And after heat equation, I'll be talking about some variational methods or some more things about Sobolev spaces, and I'll connect the variational methods to optimization, and we'll basically solve some particular optimization problems where the dynamics are basically governed by PDEs. So that's how where we are headed. So basically, I think in the month of June, this week I'll finish Laplace. In this lecture I'll finish Laplace equation, and even in the month of June I'll be finishing Laplace equation, elliptical equations, heat equation, variational problems, and I guess with that. And once I'll just recall the Sobolev spaces and distributions and weak derivatives once again. With that, I'll end our discussion on PDEs. In the month of July, I'll basically start with optimization, linear algebra, and probability. So far, we are dealing with some rigorous math because it's of partial differential equations. Once things are in machine learning domain, things will be less abstract and very smooth. So because I have promised Raghu sir that some of his students are basically solving PDEs using neural networks, I had to teach all these concepts. Okay. So I'll just recall some of the properties of harmonic functions that we have taught in last class. So basically, Laplace equations remains invariant under rotations something that I have given as an exercise. I hope you solved it. Okay, and I guess we have talked about the fundamental solution of the Laplace equation. Del phi x is equals to minus 1 by 2 pi log mod x, or 1 by n into n minus 2 okay, 1 by n minus 2 omega n is basically the volume of unit ball, n minus 2 if n is equals to 2 greater than or equal to so this is basically the solution of del phi equals 0 on Rn minus 0. So this is called the fundamental solution. I mean, because we have also spoken about distributions and stuff, del phi on Rn, where delta naught is the Dirac delta function. Just let me solve something. Square by dou u r square. Let me solve the Laplace equation in 2 by r dou u by dou r plus what is Laplace equation in spherical coordinates? Just a second. Okay, let's get into that later on. Okay, now we basically okay, let phi be the solution of be the fundamental solution as defined in del phi equals 0 in Rn minus 0. We define this convolution. We have spoken about convolution in length in previous lectures. Basically, if omega is our domain, okay, sorry. Convolution is basically this expression. Integral, I'm recalling. We are defining this particular thing. So if we differentiate, if we apply Laplacian operator both sides with respect to x, so we would expect something like this to happen. But this is not the case until this is true if and only if f belongs to L loc, if it is only locally integral function. We have talked about this in length while I spoke about distributions. Okay. So uh, note that phi has an phi basically has similarity at x equals 0, and we want to basically understand uh, the singularity of 1 by that is we want to basically some ball around 0. This should be finite. This is true if n is greater than or equals to 2, right? Okay. So now I'm just going to define some things. So basically integral of b1 of 0. This is basically integral of unit ball is equals to volume of unit ball, which is basically something called measure on unit ball, which we denote by omega m. So this is volume of unit ball in Rn, and integral of d10 dx. This is basically of b. This is unit ball. This is radius r. So basically this is r power n into b1 of 0 into dy. So which is equals to r power n into omega n. So these are some identities. Please check. Please check. Okay. Similarly, we basically take the surface integral ds1. These are some identities on multivariable calculus. If people are not that familiar with these identities, please let me know, and I'll just revise multivariable calculus again for you guys. N times omega n minus 1. These are some identities that we have to keep in our mind. So now, if u of x equals integral Rn times phi of x minus y f of y dy, phi is locally integrable and f is continuous with some compact support, implies dx u. This we have discussed in length in distributions discussion. Phi of y into del x, and this is something that you get if you change the order of integration, implies del u is equals to phi star del f. So now I'll just state a theorem. If f is twice differentiable with compact support on Rn, and phi is the fundamental solution, and we define u to be convolution of f star phi. So basically your u is also solves the your Laplacian, your Poisson's equation. So the solution of this implies, I mean u is convolution of f into phi star will basically solve the Laplacian equation, Poisson equation. Okay, so this is one theorem. So before we jump forward, I would like to recap some multivariable calculus. Okay. Recap of multivariable calculus. So firstly we'll talk about line integrals. So you basically have a curve, say this. So you basically find out the length of the curve this way. So let this be delta x and this be delta y, and your usual Pythagorean theorem delta z equals del x square plus del y square whole power half. And now to just bring out your del x outside, del y by del x is tangent square into del x. So implies is an integral of length is basically integral of 1 plus dy by dx whole square whole power half into dx. This is usual trick that you might be knowing to find out the line integrals. So similarly, if let us say it is in some n dimension, so you parameterize your curve in n dimensions from gamma a comma b to Rn. So your length of the curve gamma is basically given by integral a to b d gamma 1 by dt plus d gamma 2 by dt, so on. Obviously you'll be having squares, square plus so on to d gamma n by dt. This is the length of the curve. So let us say you want to integrate a function on a curve p of x comma y dx plus q of x comma y dy. You integrate it this way, 0 to b, p of gamma 1, gamma 2, gamma 1 dot plus q of gamma 1, gamma 2, gamma 2 dot dt. So how you integrate a function on a curve. Just a second. Okay. So now I'll speak about the surface measure. So to understand a surface mathematically, you need this a set basically map every point of your 2D surface to some integral like this. So you usually represent your parametric curve by this thing. Such that x is equal to So in order for your integral to make sense, this will be going into some higher concepts of differential geometry, which I don't want to. Just that you define your J1 basically Fu, Fv, determinant of this should not be equal to 0. They must be linearly independent to find a surface measure. So you define your J1 and J3 so if your determinant all this should not be equal to 0 in order to find your surface measure. So area on the surface is basically given by this particular expression. Area is basically given by integral b j1 square plus j2 square plus j3 square whole power half du dv. And if you want to integrate a function over a surface, integral s times f of u comma v into j1 square plus j2 square plus j3 square du dv. So now we come to the Green's identities. So I'm just recalling the integration by parts rule. This all of you must be familiar with this. This is for one dimension case. So we would basically would like to extend these notions to higher dimensions. Okay. So this is one of the Green's identities. This line is equals to integral over surface and this in arbitrary n dimension can be written as, this is something called Stokes' law. And now I'll just state some Green's identities without proof. Integral del u dx these notions will be helpful in solving Laplace equations in few moments. Here V is the unit normal. Okay. Okay. I'll just state the theorem. Then these are some identities. I have given detailed proof of this and just in notes, but I'm just because we are engineers and we don't need all that stuff. Yeah. So I guess with this formula we can solve the Laplace equation. So today I'll end the class with this.